basically what we're going to add today is multiples of multiples. So different ways to add just more of the same thing. So you're not going to see any groups you haven't seen before. There's just going to be putting a whole bunch of stuff on a bunch of stuff. So it's a pretty just nuts and bolts kind of one. It's not a lot of big theory into this one. Just some rules and some practice. And also through today's class, I'll give you the units formal assignment. You can start working on it. Obviously, there will be things on that assignment that you haven't learned yet. So if you look at that and go, oh, just skip it. There's lots that you can do. And so you'll be able to make good headway on it without me waiting till the end of the chapter before I give you the assignment. So you can start working on it whenever you have your time. For us today, let's get on with the words that we need to write down in the blanks. There can be multiple sets of multiple bonds in a single molecule. So lots of multiples. Multiple sets of multiple bonds. Now, I think I'm going to be really nice to you guys and either have double bonds or triple bonds. There is rules. I talked to someone and we did find that there are rules for putting doubles and triples in a molecule, but I think that all of my examples will stick to all doubles or all triples. I think that'll just make life easier. There can be multiple hydroxyl groups. Multiple hydroxyl groups, which is, what's a better name for hydroxyl group? Big silence. Let's try it again. Hydroxyl groups. What is a better name for hydroxyl groups? Alcohols. Alcohols is what we're doing. So that's alcohol. So you can have more than one alcohol in a single group. Rules for naming all of these are similar to the other ones. We're just going to put more and more things together. Similar, basically the same way. When we have multiple double bonds, which are alkenes and alkynes, the double bonds are always on the parent. So we don't have a way to use a double bonded hydrocarbon as a group on a bigger alkane. So if we put if there's a double bond in the molecule, it is part of the parent chain. It is not a functional group added to a parent chain. So we use all the fun prefixes we've learned, di and tri and tetra. I think that's all I'm going to be able to fit. Yep, etc. And before the "ene" ending, "ene" or "eine" ending. So you will turn into like dienes, trienes, tetraenes, dienes, which is funny, or trienes, and other words that we still use all of the, when we're saying them out loud, we break up the prefixes into their sounds. We don't try to mix their syllables because that will make it somehow even worse. Pause. Continuing on, we use the lowest numbers like we always do. So let me slide this up so you guys can see better. We use the lowest numbers. To identify the location of the double bonds, if we can choose a different set of numbers that has lower numbers, those are the better numbers. And we always choose our total set of numbers to be the smallest that they can be. We also must use a cis or trans label if it needs it. If those isomers around those double bonds need it. First example is 1,3-butadiene or buta-1,3-diene. These are both good phrases. I prefer the first one personally, but they're both correct ways. You could basically put the number closer to where the important pieces are or further away. So we're going to need a little zoom in here for my particular drawing. So we have a parent chain of 4 carbons and 2 double bonds. So this thing in here, this diene is 2 doubles. That's what that's trying to tell us. So the diene is like 2 enes, 2 double bonds. So what we're going to draw here is 1 and 3. So we have 1, 2, 3, 4. So it's going to be a double bond between 1 and 2. So I'm probably going to draw it like this. And then down, and then double bond, and then that's it. I think that's it. Is that enough carbons? So I got 1 carbon, 2 carbons, 3 carbons, 4 carbons. All right, so I have, that's it. That's the whole molecule. I can draw the hydrogens on this if I need to. So I'm just going to draw them in green because it's like, right now, this would be an acceptable line drawing. This is done. But to show where the hydrogens go, they go here and here and here and here and here and here. Now, is this one cis or trans? So, neither cis nor trans for this one. Same, no cis or trans in our next one. Slide it over and go through 1,3-butadiene, which is awkward to say out loud, but I think we figure it out. So we need 4 carbons and triple bonds between 1 and 2 and 3 and 4. So this one's going to be pretty fun. We're going to do, let's just do a different style because it fits better. C, triple bonded to C, single bonded to C, triple bonded to C. That's it. That's the whole molecule. It's pretty fun too because there is actually only a hydrogen there and there. That's it. This is weirdly, because of all these massive bonds, it's actually C4H2 as like a molecular formula. There's more carbons than hydrogens in this particular molecule. If I did a fancy line diagram, I could also do this. You don't have to do both, but you can see both. It would be really fun because it's just this triple bond, single bond, triple bond. That's the whole molecule. Nice and symmetrical. Looks like a dumbbell to do some lifting with. But otherwise, that's our whole thing there. Okay, we'll slide down and we're going to have trans 1,3,5 hexatriene. Pretty cool. So this is telling me I have 3 double bonds here. The triene, 3 double bonds, and one of them is trans. In this case, the only one that's going to be trans is the middle one because it's the only one that can be. The other ones will have 2 groups on one side. They can't be cis or trans. So only the middle one can. So I'm going to start in the middle here and see if I can draw it. So I'm going to draw my double bonds here, up, and I'm going to draw trans here. This is my basic trans starting skeleton. So then I know I have a double bond on this side and a double bond on that side. So let me just keep drawing this. Yeah, that's it. So this is trans 1,3,5 hexatriene. If I were to number them, I could go 1, 2, 3, 4, 5, 6. Those are my 6 carbons for the hexa part. There's 3 double bonds. That gives me my triene. And this one here is trans. The middle one is trans. This double bond and this double bond have 2 hydrogens on each extra end. They can't be cis or trans. This one in the middle can be trans. Because it's got a big group on one side and a big group on the other side. So basically saying this group is trans, this double bond with this group. And we'll see the comparison because we're going to draw the next one is cis 1,3,5 hexatriene. It's almost exactly the same molecule. The only thing we're going to switch is the orientation of this double bond. So this middle double bond is just going to switch from being down here to up. That's all that's going to change. So let me slide over in my little diagram here and draw the same thing. I'm going to start in the middle. And my double bond is going to be both ups for cis. Both down also works perfectly good, but the same side is all I'm working with here. So then my double bond is going to come out on this side, and the double bond is going to come out on that side. So this will be the cis part of the 1,3,5 hexatriene number 1, 2, 3, 4, 5, and 6. So that gets my 6 for hexa, 3 double bonds for triene, and the cis part is in the middle, where this bond and this bond are on the same side of this double bond because it can't spin. All right, I included the next one just because it's a rather ridiculous diagram. It's a fun little molecule. So we can make this 1, 2, 3, 4 pentatetraene. It does sound icky, but let's think about what we can break this down into. How many carbons are in the parent chain? 5 carbons in the parent chain. How many double bonds are there? 4. So all double bonds. So we have a carbon. Let me put the color on here. Carbon, double bonded to a 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 carbon. And then there's hydrogens on the end. So this is a weird molecule that would be C5H4. And again, more carbons than hydrogens in this particular molecule, which is generally not the pattern that most go. I don't know how I would go around actually synthesizing this particular compound. I don't know if you could actually make a jar of it, like you could get a sample of this thing. I don't know, but this would be the correct structure and name of it. This follows all the rules. What do you mean? Like just lines? Yeah. Lines would be tricky because it's basically just that's it. That would be line diagram. 4 sets, and that's where you'd really want to make sure you got a little gaps between them. It's just 4 sets of carbon bonds because it would be then carbon 1, 2, 3, 4, 5. Yeah, that's how it would work. No, this will be straight. It won't be a W. You could try making it if you broke up the molecules. You could double bond to double bond to double bond to double bond to double bond. It would be a straight line molecule. It wouldn't W. I could make it maybe a little later. I'll make this one because I think it's fun. Any other questions? That was a good one. So let's take a look at, we have some circles and some more branching things. So we have some functional groups in this one. So we have our, let's see if I can draw it here, see how good my drawings are going to be. My parent chain is going to be the one that includes all the double bonds. So that's my parent chain. So I'm going to have a methyl group on the outside. I have to number it to make my parent chain the smallest it can be. So I'm going to do some numbering here. 1, 2, 3, 4, 5, 6, 7. So I have my parent chain. So I've got, let's see if I can get this all listed out here. So 7 carbons, 2 triple bonds. My triple bonds are at what place? Where are my triple bonds at? 2 and 5. Yeah, the triple bonds are at 2 and 5. What else do I have? Yeah, I have 1 methyl on where? On carbon number 4. So this is just me listing out what it's going to be, and now I will make the name. It's a good idea to kind of list out your requirements and all the things that need to be in this name, and then go from there. Because then you can probably write it more in the front ways instead of writing it backwards. So what's going to come first is my group. So my first words is 4-methyl. And then I need to do, where are my triples? 2 and 5. And then what is my base? Hept. And how many triples do I have? Yeah, so hard to say. Hepta, di, ine. Yeah, there we go. That's the way I like that one. So I've got a 4-methyl group stuck to my 2,5-heptadiene. That still covers all the fancy words. Let's do the next ugly circle. It's it almost looks like a heart, but it's a big cyclo compound. Where should I start numbering my cyclo compound? At the triple bond, start there. There's no other group, so we're not actually going to use these numbers, but it's also helpful to figure out how many there are. Start here at 1, so that's going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's an 11 circle. Do you guys remember the word for an 11 group? Yeah, it's undeck or just like 110. It's real boring. I don't know if it would be unideck, but I think it's undeck. But I don't think there's an I in it is basically the difference I'm saying here. So uni might be not terrible, but I think that's... So alcohol has a higher priority than all the double bonds. So even if there's double bonds in it, we number them so that whichever number the alcohol gets given is the smallest. So we number according to the priority group, in this case is alcohol. Use prefixes like we've done before to show the location of the hydroxyl groups. Hydroxyl groups will always be on the main chain. For us, this is just how priorities work. The main chain will always have the alcohol in it. So wherever you're drawing chains, the alcohol has to win. Yes, butanediol. This is 1,2-butanediol. So let us look through what we're discovering about this. So we have a diol. So this means 2 OH groups. So I'm just right beside here, we have 2 OHs. What else do I know about this? Butane, geez. 4 carbons. Do we have any double bonds? No. Why do you know that? Because I'm looking at this particular an. So this is an alkane. So it's all single bonds. So it's the butanediol, not butanediol or butanediol. Well, it get a real big marble mouth after eventually this. Next. Yeah, that's it. Go on. 1, 2, 3, 4. And then we have alcohol on 1, OH, and 2, OH. That's it. It does look weird because this is actually 1, that's 2, 3, and 4. Yeah, the way this particular works. Next one, cis hex 3-ene 1,6-diol. Isn't that awful? It's an awful thing. So we got to break it down and find our parent chain. Parent chain is the hexes. 6 C's. 1 double bond on 3, and it's cis. 2 OHs on 1 and 6. So this is great. So that's my list of things I need to put in this molecule. So I'm going to start with the cis because I think that'll make my picture the best. So I'm going to start in the middle weirdly with this molecule because I think it'll make it work out. So I'm going to start on the 3,4 and make my cis molecule first. So I'm going to start with my double bond, and I know I'm going to go down on both sides because I know I'm going to have a cis molecule. Do a little sneaky numbering here. I'm going to say that's a 3 and that's a 4 because I know my double bond is on 3. So then this one would have to be a 2, this one would have to be a 5, and so on. So I need more carbons to fill out the rest of this molecule. So I'm going to go this way, and then I'm going to go that way. So now I have the carbons 1 and 6. So now I know where to put my alcohols. I'm going to put them kind of up to the side here. 1 here, I'm going to write O, then H this way. And then this one, I'm going to write O, then H that way. So now I have 2 OHs on 1 and 6, 6 carbons altogether, 1 double bond on 3. And that's what I have here. Good so far? All right, one more. Is this one a benzene? Yes. No, it's not a benzene. That was a trick question. It's not a benzene. Why is it? It's almost a benzene. What's it missing? It's short one double bond. So this is a cyclohexanediene. Isn't that awful? Yeah, it's not a... And this is why we call them benzene and not cyclohexyltriene. Because that's worse. It's worse and it's really common. The benzenes show up all the time, so we have a fancy name for it. Next one. We have to number the alcohol first. I got one left. Let's keep it through to guys. So we're going to have a 1, a 2, a 3, a 4, a 5, and a 6. We have to do the alcohol numbered once. So my double bonds are on this one and that one. So we have 6 carbons, 1 OH on 1. We have 2 double bonds on 2 and 5. So now we can put a name together. It's a big mess. So we've got an OH, so we have to end in all. We've got 2 double bonds. We've got 6 carbons. We have a cycle. So this is going to be the big mess. Oops, back to the right size. Yeah, this thing. This is 2,5 cyclohex hexadiene. There we go. Cyclohexadienol. All right, so to break this all down, we have this one here, 1 OH. This one here, this is 2 double bonds. This is 6 carbons. This is a ring. And this is where? Double bonds. Location. It's right here, location. Double bonds. So that's where all of the pieces of that name come from. I have 2,5-cyclohexadienol. So it shows me I've got 2 and 5. It gets my diene, which is really nice because I actually get this. These are connected here. Annoyingly. So since those are connected, I could possibly put this in here. So it's totally fine if I went cyclohexa-2,5-dienol. That's also fine. You can kind of shift the numbers around in the words and still be okay. That kind of follows what we did on the first page. Now that's a whole lot of me talking.